everyone, Dr. Zach is back. So you've had time to practice finding the derivatives of inverse trig functions. Now it's time to think about antiderivatives. So let's get started. So today's lesson preview was to help remind you how to find the values of arcsines and arctangents, and to be reminded that there are domain restrictions when working with arc problems, unlike when you are working with inverse problems. Now, the arctan, you are asked to solve for x. In order to undo an arctan, you basically want to figure out the tangent of both sides, and then you will solve your equation. So let's look at some algebra before we begin our antiderivatives. For example 1, we want the exact value of this complex expression. So what we'll do is we'll allow y to be equal to the cosine inverse of negative 1/3. So we then know that the cosine of y must be equal to negative 1/3. Now let's think about our right triangle trig. Right triangle trig will say that if the angle is y, then the cosine is going to be the adjacent over the hypotenuse. And we can find that missing side is the square root of 8. Now how does that help us? We're going to rewrite our original problem as the tangent of y. Using the same triangle that we drew for the cosine function, we know that the tangent of angle y is the square root of 8 over negative 1. So our complex function is really negative 2 root 2. So now as we look at example 2, we want to rewrite this expression in an algebraic form. So let's follow a similar idea. Let y equal the arc cotangent of x. So then the cotangent of y must be equal to x. So if once again we draw a triangle to represent what's happening, right triangle trig, and we have angle y, a cotangent is going to be the adjacent, which is x, over the opposite, which is 1. And we know that the hypotenuse is going to be 1 plus x squared. So if I go back to my original problem and rewrite this as the cosine of y, using my triangle, this is going to be equal to the adjacent, which is x, divided by the hypotenuse, which is the square root of 1 plus x squared. So as you can see, we can take these complex expressions, which are combinations of arc problems and non-arc problems, and simplify them so that we might be able to use them in multiple ways. So for example 3, I'm given that y is the arcsine of x. I also have my domain restriction. I'm looking for the cosine of y. Well, rewrite my problem so that the sine of y is equal to x. And if the sine of y is equal to x, that means we can draw a right triangle again. Sine is going to be the opposite, which is your x, over your hypotenuse, which is 1. And we know that our missing side is going to be 1 minus x squared. So then what is the cosine of y equal to? That's going to be your adjacent side divided by 1. For example 4, I'm looking for the tangent of y. We're going to follow some similar ideas. We can rewrite our problem. Secant y is equal to x. Draw that right triangle. Label the angle y. We know that for this one, we're going to have the hypotenuse divided by the adjacent and be able to figure out that opposite side. And the opposite side is going to be the square root of x squared minus 1. So then what is the tangent of y? Tangent of y is going to be equal to your opposite, which is x squared minus 1, divided by your adjacent, which is 1. All right, I have 6 questions that I want you to practice this algebraic manipulation. Turn off the video, practice, and then check your answer. All right, so check through your answers for numbers 22, 30, 32, 34, and of course 36. 36 actually came up with 2 answers. It was a little bit more complex. So for number 5, you're going to show that the derivative of the arc sine is 1 over 1 minus x squared. In order to do that, let's let y equal the arc sine of x. In which case, we know that the sine of y is going to be equal to x. Let's find the derivative. We get the cosine of y dy dx is equal to 1, or dy dx is equal to 1 over the cosine of y. However, we cannot leave our answer with y's in it. Let's draw our triangle. We are given, or figured, that the sine of y was equal to x. So here's my y. We'll have the opposite over the hypotenuse. Square root 1 minus x squared is the missing side. So what is the cosine of y? That's going to be 1 over your adjacent divided by your hypotenuse. All right, so if we have the derivative, that means you should also know the antiderivative. But let's look at the derivative of the arctangent of x. We know the answer is 1 over 1 plus x squared. What if we were to let y equal the arctangent of x? And then we know the tangent of y must be equal to x. The derivative of the tangent is secant squared y dy dx is equal to 1. So dy dx is 1 over the secant squared of y. Think about that triangle again. Setting up the tangent of y is equal to x. That's going to be the opposite over the adjacent. And our missing hypotenuse is 1 plus x squared. So if we substitute for the secant of y, which is going to be the hypotenuse divided by 1, and then we square it, we get 1 over 1 plus x squared. So you've had some experience with the derivatives of inverse trig functions, and now you know how to solve them. The integrals, though, come from those derivatives. You're also going to need to know those antiderivatives. So let's look at example 6 for a minute. You need to be able to look at each problem and think about which formula or antiderivative it looks like. Notice we have 4 minus x squared in your denominator. When we take a look at all the formulas that we've been practicing with, here's your denominator. The one that has a number minus something squared is an arc sine. So that we're going to tend to try to find an arc sine as our final answer. So if we were to let u squared equal your x squared, and we let a squared equal the 4. Let's see what happens. U is equal to x, so du must equal dx. If a squared is 4, a must be 2. Rewrite our problem, we now have du over the square root of a squared minus u squared, which is the formula for the arc sine. So we know our answer is going to be the arc sine of u over a plus c. But what was u? You're going to have the arc sine of x divided by your a value, which is 2, plus c. So we need to recognize these problems. So for example, 7. We have dx over 2 plus 9x squared. When you take a look at the list of problems, it looks rather like an arctangent if we can determine the a and the u. So in this problem, if we let a squared equal 2, then a must be the square root of 2. If we let u squared equal 9x squared, or u equals 3x, du must be 3dx. Solve for dx, we get du over 3. Rewrite the problem. We have 1/3 the antiderivative du over your a squared plus u squared, which you know is 1/3 times 1 over a, arctangent u over a, and don't forget a plus c. Filling in your u and your a values gives you 1 over 3 root 2 times the arctangent of 3x over your square root of 2 plus c. So now check out example 8. If you're thinking that example 8 kind of looks like an arcsecant, you would be right. So let's start with letting u squared equal 4x squared. U equals your 2x. du is going to be equal to 2 dx. So then dx is 1/2 du. And that leaves us with a squared equals 9, or a equals 3. Now we're ready to do our substitution. We have 1/2 the antiderivative du over, now wait, what was x equal to? That's going to be a u divided by 2, square root of your u squared minus a squared. So we clean it up a little bit, and we're back to du over u square root u squared minus a squared, which you know is that arcsecant. So we will have 1/3 arcsecant, the absolute value of 2x divided by 3 plus c. And for example 9, notice once again it's got a square root, there's an e to the 2x. I'm not sure what's happening with this one, but I'm going to let u squared equal e to the 2x. U is equal to e to the x, du equals e to the x dx. So then dx is du over e to the x. And you know what? Let's let a squared equal 1. So a is 1. If we do our substitution, we'll get du over e to the x square root u squared minus a squared. Oh man, look, we've got that extra e to the x. But isn't e to the x equal to u? So we rewrite our problem one more time. This will be du over u square root u squared minus a squared, which really looks like an arcsecant again. And we'll have the absolute value of e to the x over 1 plus c. But we don't really need that absolute value. So for number 10, I might try u substitution. If u equals x squared minus 4x plus 7, du is 2x minus 4, which is not in the numerator. So you see my problem here. Now, what I'd like you to recognize is that the numerator has an exponent of 0, and the denominator essentially has an exponent of 2. When you see that, you might be thinking about an arctangent. So you want to tend towards that arctangent. But you're going to have to complete the square in order to get the right form of your problem. So we want to complete the square for x squared minus 4x plus 7. So here's your reminder. X squared minus your 4x. Now take the 4, cut it in half, and square it. So this would be 2 squared. Now you can't just run around adding the number 4, so you're also going to subtract 4, and we still have a plus 7 in the problem. So essentially what we did is we added 4, subtracted 4, which didn't change the problem. So that'll give us the quantity x minus 2 squared plus 3 when we rewrite the problem. So go back to the original problem. We rewrite it using algebra because algebra is the best. We have our quantity x minus 2 squared plus 3, and we're going to let u squared equal x minus 2 quantity squared. U is your x minus 2. Du is your dx. A squared is going to be equal to 3, so a is the square root of 3. Substitute, we have 1 over u squared plus your a squared du. And of course you know that that's going to be the arctan, so 1 over root 3 arctangent of your u value, which is x minus 2 over the square root of 3 plus c. So completing the square is an excellent skill to have. If you need a little bit of practice, make certain you get it. So for number 6, once again, you're going to have to complete the square. I'll help you with that piece. When you have negative x squared plus 3x, before you do anything else, factor the negative out. You're left with x squared minus 3x. Cut your 3 in half and square it. But did you really add? Nope, that was subtraction. So you add your 3 halves at the end as well, which means adding 9/4 because it was squared. So now when we go back and rewrite your problem, you would have f of x is equal to 1 over your square root of x minus 3 halves quantity squared plus 9/4, and you should have a negative in front of that square root. All right, for number 11, that looks familiar. This shouldn't be any problem for you at all. So you're going to take your integral from your values of 3 halves to 9/4, since we're looking for area. And you're going to have 1 over your square root 3x minus x squared dx. Use that problem as we rewrote it. Your answer when you're finished should come out to be a pi over 6, but just make certain you practice. For number 7, notice you've got this very complex problem. You might want to make it as 2 problems. You'll have x over square root 4 minus x squared dx plus the integral 2 over 4 minus x squared dx. Your final answer should involve, oops, I lost my square root, put that back, should involve an arc sign for the second part and u sub for the first part. All right, finish up that problem, please. Today's lesson practice, I want you to look at page 372. Make certain you know the derivatives of your inverse functions and how to find the antiderivatives. That's it for today's lesson. You have a fabulous day.